Welcome back. Today, we are diving deep into the story of fuel. We're going to trace its incredible journey, all the way from its raw form, hidden in the earth, to the spark that literally powers our modern world. So let's get into it.
You know this sight, right? The little blue flame on a gas stove. It's so common we barely even notice it. But that tiny flame, that's a powerful chemical reaction in action. It's a reaction that has truly shaped human history. And yeah, it still drives pretty much everything we do today.
But what is actually happening inside that flame? To get to the bottom of that, we have to ask an even more basic question. What exactly is a fuel in the first place?
Okay, so at its core, a fuel is just any material that stores chemical energy. You can almost think of it like a battery, but instead of storing electricity, it's holding onto potential heat, all locked up in its chemical bonds, just waiting for the right moment to be released.
And that release? Well, it happens through a process we call combustion. You see, when you add a little oxygen and a spark, that fuel goes through this super fast chemical reaction. Its atoms all get rearranged, they form new stuff, and boom, that stored energy is let loose as heat and light. It's a surprisingly simple recipe for a reaction that completely changed the world.
But here's the thing, fuels come in all sorts of shapes and sizes. So to make sense of it all, we basically classify them using a couple of key characteristics. Think of it like a fuel family tree.
So the first big split in the family tree is all about their origin. Do we find them just ready to go out in nature, like wood or crude oil? If so, we call those primary fuels. Or did we have to manufacture them from those natural sources, like making charcoal or gasoline? Yep, you guessed it, we call those secondary fuels.
This is the perfect example, really. You've got wood, a primary fuel, straight from a tree. But if you heat that wood up without much oxygen, you create charcoal, which is a processed secondary fuel that actually burns hotter and a lot cleaner.
The second way we classify fuels is way simpler. It's just their physical state. Is it a solid, like coal, a liquid, like diesel, or a gas, like the natural gas that might be powering your stove right now? Each one has its own unique properties and, of course, its own uses.
Okay, so we've sorted them into categories. But how in the world do we get from a raw primary fuel? I mean, think about that goopy black crude oil, to the very specific secondary fuels we need every single day. Well, let's follow the journey of petroleum.
The magic, and it really is like magic, happens inside one of these, a fractional distillation tower. It's this absolutely massive industrial column that basically cooks crude oil to separate it into all its different parts, or fractions, based on their weight and boiling point.
It all works on a pretty simple principle. Different things boil at different temperatures. So the crude oil gets superheated, and all that vapor starts rising up the tower. As it goes up, it cools down, and different parts condense back into liquid at different levels. The heaviest, gunk-like stuff stays near the bottom, while the lightest, like petrol, makes it all the way to the top. And if you could peek inside that tower, you'd see these special things called bubble trays. They're engineered so that the hot vapors have to bubble up through liquids that have already condensed. This forces this constant cycle of evaporation and condensation, which gives you a really pure, clean separation of everything from heavy lubricating oil at the bottom to gasoline way up top. All right, so now we've separated out a specific fuel. How do we know how much energy it's actually packing? How do we measure its bang for the buck? For that, we use something called the calorific value. It's basically a score, a number that tells you exactly how much heat gets released when you completely burn a certain amount of that fuel. Simple, right? Higher calorific value means more energy.
But there's a little catch. You've got the higher calorific value, or HCV, which is the absolute theoretical maximum amount of heat you can get. But in the real world, some of that heat always gets wasted, turning any water in the fuel into steam. So the lower calorific value, or LCV, accounts for that loss. This might seem like a small detail, but for engineers designing an engine or a power plant, the LCV is everything. It's the practical, usable energy they can actually work with. Okay, let's bring all this theory back down to earth for a minute. You've probably seen signs for CNG at a gas station, and you've definitely heard of LPG for a barbecue grill. So what's actually the difference between these two common fuels?
You've seen them both around, CNG at the pump, LPG in those tanks for the grill. But even though they both do a similar job for us, they're chemically pretty different, with totally different origins and properties.
The main difference really comes down to what they're made of. CNG is exactly what its name says. It's natural gas, which is mostly methane, that's been compressed to a really high pressure. LPG, on the other hand, stands for liquefied petroleum gas. It's a mix of other stuff, mainly propane and butane, that turns into a liquid under way less pressure, which is why it's so easy to store in those familiar tanks.
So, why does any of this matter to you? Well, CNG is becoming more and more popular because it's seen as one of the cleanest and cheapest fuels out there. It pumps out fewer pollutants, and its high ignition temperature actually makes it safer than regular gasoline in a lot of situations. So when you step back from the simplest log on a fire to the super complex gases we pull out of those giant towers, the whole story of fuel is really the story of us, of humanity getting cleverer and cleverer at unlocking the chemical energy that's been stored all around us. Think about it. These fuels are the very foundation of our modern world. And what are they really? They're essentially ancient sunlight, captured millions of years ago and stored in the earth. And that leaves us with a really big question to chew on. As we keep using up all this incredible energy from the past, what are we going to use to power our future?